All right, thank you everyone for coming. There's the microphone. Okay, so my presentation will be about developing the actual model that goes into what everybody's been talking about. So most of these talks have been about the final product that's been made. This is how to actually, the engineering behind the model that's been made. So the technique that we're going to be discussing is called the 3D linear method. I pioneered to put templates across a road in the most effective and efficient way to save the most amount of time on a project, which everyone knows that time becomes money. So a little bit about myself. As you can tell from my voice, I'm actually from Australia. I moved here in 2014, but my experience does span across 4 different countries, and I've worked on many different large-scale infrastructure projects similar to the jobs that Cameron presented, and everything from desalination plants to power stations to multi-level viaducts. A little bit about the company I'm from, TERRA Engineering. We are starting to develop our footprint in doing 3-dimensional design, and we've actually begun to train other firms in these techniques to be able to build their models in the most effective and efficient way. And we're also even trying to train the Illinois Tollway themselves and actually in their ability to analyze the models we give them. We also understand how these investments come into play to increase the efficiency and effectiveness. Those 2 words are going to come into play throughout this presentation. So why do we develop visualized models in the first place? And the primary purpose is to convey the intention to the community and the client. What you see on the left is a rendered model of a project that I worked on in Adelaide, South Australia, called the Urban Superway. And the picture on the right is the actual photograph of the same junction. So the advantage of that rendered model before it was built is the client was able, the client being the Department of Transport and also the community, was able to see what was there before it was built. However, that is not the primary purpose of why we build models. So why do we build models? The primary purpose is to make a centralized data source for all the information. This way, plan production, quantities, option development, eventually automatic grading machines, and visualization is a subcomponent to that. But this way, all the data can come from one source, and you're always guaranteed to get the result to be clean every single time, not the product of the visualization result. So the engineering application is really the true primary purpose of why you build these 3D models. These investments in 3D lead to much more increased efficiencies and effectiveness because we're able to make these products in one piece, and then the outputs come from that model rather than traditional way of building the outputs and then making the model from that. We have one centralized model, one place to make the changes, as people who know Lord of the Rings, one ring to rule them all, one model to control everything is the idea behind the purpose of building a centralized model. So, how are these models developed? This is what the current teachings will demonstrate. If you open up any package of a Bentley product or an Autodesk product out of the box, is to build one corridor per alignment. There are pros and cons to this approach. The pros being you get one corridor per alignment to get a simpler representation of the road. However, the cons, that's just a small part of the cons, but the biggest part I want to mention is the stuff in red. The road changes so often along the road that the templates you need to build are so complicated that only the person who made them can edit them and change them, because design builds, especially large projects, they change every 10 minutes about what they feel like on the road. So in order to be able to change the products, these templates need to be so comprehensive to cater for every scenario, it's too complicated. And if that person is hit by a bus, that person's sick, that person leaves the company, who's going to amend the template? And what I find is on some consultants, the person who built that template can't fix it 2 months later because they forgot how they built it. So is there a better way? Well, that's why we're here. 3D linear method is a clean way of building the same data but with simpler templates. It's based on the exact opposite of what's the current out-of-the-box thinking of one template. Multiple corridors, you keep recycling the same template. For those who are familiar with the old school way of designing, criteria files may mean something or may not. What a criteria represents is a group of code of a simplified element, such as a curb, a pavement, a sidewalk, a parkway. I was about to say verge, but that's a very Australian term. Just bits and pieces of the road. That's the limit of the corridor, not further than just the simple cross-sectional element. Every single piece connects to every other piece just like Lego. Each of those 2x4 blocks is a simple block, but if you get the blocks, you replicate the same blocks millions of times, eventually you get one overall model. Now that model, you can't put, if you put that into one template, you'll be still modeling it in 2100 because it's too complicated to make as one piece. But each of those pieces, a 2x4, a little 2x1 block, those pieces are easily created because of the simplicity of how they're made. So a little visualized demonstration are based on a Illinois tollway road. So 4 basic components of an Illinois tollway road, an aggregate shoulder, oh sorry, 3 components. An aggregate shoulder, we have this lane called Portland cement concrete pavement, I believe it's called. That's just the type of pavement that's used in the Illinois tollway, and an asphaltic shoulder. We have your typical section from an Illinois tollway job. Each of these pieces is a different corridor. Each of those circles is how they all connect. Because each of these pieces connect to each other, we now have a whole series of interchangeable pieces that we can change anytime we want, because sometimes you want to change a part of the road, not the whole thing. You cannot do that if it's one template. You can do it if it's multiple. I don't like that curb anymore. The client says, I want barrier. You just switch it out, reconnect. I want to put a lane in there. You insert it where you need it. And notice how the rest of the lanes have stayed consistent. So I've only changed parts of the template. Now we can go further and start to add external components to multiple roads. I want to add a ditch. I add it where I need it and connect it where it's required. I need a retaining wall and a parkway. I add it where I need it. I connect it where I need it. And oh, I need safety. I need a piece of guardrail. Better put that in there. But I only add the pieces where I need them. And I connect them where I need them. And now, in between each one of those red lines represents an interchangeable corridor where the template can change anytime you want. So now you have an infinitely complex but yet simplified design because it's all made of lots of little simple pieces. How do we manage this mess? That is an understatement. I have a job which I'll be showing at the end, which exceeds 3,000 different corridors. How do you manage that kind of database? Well, centralized data with a very comprehensive yet concise naming convention. Now, the naming convention there is specified to the tollway. On the left column, they're the feature names and the point names and the level that comes out. There is more to the naming convention that comes with it, but the idea is to simplify the convention and make it compact, so that way any software user can keep using that same convention over and over again. So how is this better than building a single template? Well, for example, for starters, the templates are simpler. The road designer and the engineer spends all the time doing what they're supposed to be doing, designing the road, not designing the complicated template. So they've got the library of templates and they can use those templates. A lane doesn't change. The section of tollway, of PCCP and a subbase and a base course, that section has been around since the 50s. So that section it's not going to change anytime soon. You can use that template on any tollway project. A curb profile in the state of Illinois hasn't changed since the concept of curb existed, because Illinois doesn't change very often. So that template, you build it once, you use it thousands and thousands of times on multiples of projects. So you spend the time creating the road, not the template that feeds into the road. The symbology. Now, for Autodesk users, the layers that will come on. Layers and symbology and levels are all interchangeable terms. Because the templates are built consistently, the way they are visualized comes out exactly the same every time you use them, which means you can do digital quantity takeoffs en masse for an entire model if you use the same templates. It's very difficult to manage that if you build a unique template per scenario. You have to ensure the symbology matches for every point on that template. But with a simplified template, you always get a clean, reliable result every single time. You change only the parts that you need. Most of the time, the lanes are going to be the same, but what changes is the end conditions and the ditches. They're the ones that are variable. You put the effort into that, and for example, global change can now happen more effectively because you're using that same template a few hundred times. I said that pavement doesn't change. Well, sometimes it does. Sometimes this particular job will have a 12-inch pavement rather than a 10.5-inch. Sometimes the project needs deeper. You make a mass change on one template, every single corridor that's using that one template is now changed. You cannot do that in the other method of a single template, you have to go to each one and make the change. That is more difficult and more time consuming, and it can lead to a lot of mistakes. So you might forget about one, be changed on the central source, and they all get populated. And it is actually rather simple to teach. Surprisingly, connecting smaller blocks than making one big block, people get the principle rather quickly because they actually relate it to Lego. That's why I keep referring to Lego. It's that metaphor of the blocks connecting together. More people understand that better than one single template. So let's talk about efficiency of how generating this work. Complex templates, the single ones, do take longer times to process because the computer has to run through every single scenario, and the more components within that corridor, the more time it's going to process and the more computing resources it's going to take. Not everybody can afford 2,000 terabytes of RAM and a 400 gigabyte video card, but the complex templates require the heavy memory to make it run smooth and effective. With the simpler templates, the fewer scenarios you have to analyze, the less time spent processing and less computing resources required. Now, I've had a lot of people saying, well, okay, you got 3,000 corridors with simple templates. Is it quicker than one template? It actually is. The computing processing to run multiple thousands of corridors that are simple is effective by a magnitude of 10 compared to one template with lots of complex scenarios. That's how the program seems to work. So it does actually make it quicker to make lots of small parts than one big part. And the less processing time, the more efficient, and the more money you save. Let's talk about accuracy. So accuracy is just as important as efficiency. Because everything's broken down into the smaller pieces, you put more detail where you need it. This particular diagram on screen shows the far on the left, that's the lane. The middle part is the gore, then there's a ramp, then there's another shoulder, then there's a curb, then an aggregate shoulder, then an end condition. Notice all those horizontal strokes represent different intervals of template drops. I don't need the detail on the main line because the main line is a very simple straight grading, but I need more detail on the gore. So because each piece is this independent, unique corridor, I apply detail only where you need it, and you don't apply detail across the whole length. If you have a single template, you want detail on one part of the corridor, you need to apply detail on the entire width of the corridor. That increases your processing time and increases the chance of computer crashing, and therefore it adds the time to build the model, and it costs more money, and then you don't meet deliverables. But by having a smaller piece, you're able to apply the detail only where you need it. And the more detail you have, the more accuracy, which is pretty straightforward. So in summary of what this method represents, lots of pieces, simple design, everything joins together. The more efficient you have, the less processing time you have, and the accuracy is only applied where you need it on the job because it's broken up into the smaller pieces. While you're thinking of questions, this recent publication about the return of investment, the idea of the 3D linear method ties directly into this because it builds the model in a quick processing time. So I will demonstrate a model that is being developed. The model construction time, it's a little bit of an understatement because it was 3 operators with a couple of months, but that was also designing as well as creating the model. But if we knew the design from the start, it's about 40 hours because it's a multi-level interchange. So let's go into it and have a look while you're thinking of questions. So are there any questions while I'm bringing up my lovely little model? Where's my mouse? Oops. So this here is the 3,000 corridor beast. Multi-level interchanges, retaining walls, all the super is done, all the lane pavements are done, the barriers are done, all the end conditions are all correct because it's based on what the engineers wanted. The parts that aren't in there are utilities because another program comes and superimposes on that, and the substructure of a bridge because another program comes and superimposes on top of that. But all the civil elements are there. It's a concept phase, so we didn't bother modeling the rest of the guardrail, but we got most of this job. And you can see, you can zoom in, have a look. Each of these pieces is a unique corridor. So lots and little pieces joined together. And because everything's consistent, I can do level symbology. Just none. I want to see, that's all my topsoil. One hit quantity, all done, because it all comes from the centralized model. You can't quite do that if you have one piece of template, because you need to ensure that each piece is correct. But while I'm babbling, is there any questions, actually? Yep.
I guess common question together, mixed. So this is a great idea, right? Building a database and then using the data from the database to then visualize. I mean, that's what GIA has been doing for years, where the fundamental is the database and then the graphics sort of feeds from it. And then what you call Legos typically, I would probably call these section 3D primitive. I'm assuming every single of these element or primitives that you're building is 3D, right?
Yeah, they actually, this is what they are. In this is an actual Bentley package, not an Autodesk package, but it's a very similar operation to Civil 3D. So let me go into, these are what the pieces are made of. So they are a sectional plane that just has a curb. So it's a cross-sectional element that gets projected along a prism using an alignment. So that's what it is. It's a 2D section that gets projected to on the third dimension. Well, actually, this is be a YX plane. Oh, sorry, a YZ plane, and then the X plane is along the. Yeah, they're extruded planes. That's how the program seems to work.
How are these assembled together? Are these visually, manually done, or is there some scripting, like for example, or you can have some rule-based, so like create this array or follow all this primitive A follows path B, things like that?
Well, there are two ways you can connect templates together. So in this program, there's a thing called a point control. So each one of these templates, let me go to a lane one. So let's see, pavement, where is it? Pavement, main line. So each one of see these little red crosses? They represent different points. Every template has a ref point here and a width point there. I connect the ref point to a width point via the interface known as a point control, which is a drop down in the program. And that width point connects to another ref, which connects to another width, connect another ref. So then that's how they daisy chain together. The other way to control it is each one of these points can be controlled via a parametric constraint, which the program can read. So that width value, by default, it's going to be reported as 12 feet to the right because it's 12 positive. If I want to change it, I insert the template into the program, and then it comes up with an option known as a parametric constraint, which is here. It's probably not going to work for me because I don't have full access to the database, but the parametric constraint, then I click on the corner and lists all the ways I can control that parametrically, then I switch the pavement over. Or the slope, I switch the slope over because I changed from what the default setting is. So that's how you can control that mechanism.
You spend more time on rather than the building side, you spend more time on the connecting points.
Pretty much. Yeah, I spend more time connecting the blocks together. That's where the effort comes in. And that's actually a lot quicker than building this ginormous, ugly template that takes a year to finish. Yep.
As far as applying texture to this, you get, take your process and wet it with Cameron's output. Is there any sort of processing or any sort of step that needs to be interjected in that to get from this model to that realistic
This is
photo,
Cameron mentioned that he can take DGMs. This is just a DGM. So you can take that model and supply skins.
It'll probably export out as a mesh, and then you can texture a mesh.
Yeah, these things are all meshes. So it can export out, and then you can make it pretty. I mean, from an engineering point of view, I prefer the solid colors because I understand that yellow is PCCP pavement, but the average builder goes, what the hell is yellow pavement? My road's not yellow. It's grey. So that's where the texture comes into play.
That's the disconnect for the public. They're like, everything's gray.
Yeah, and structure, and for some reason in Illinois, all structural elements have been rendered as pink. It's just a historic color. That's just what they do. So that's why all the bridges are pink. There's no engineering reason why it's like that. It's just a historic reason. And aggregate shoulder is red. But I don't know why it's red. It's just red. But there's strange reason. And topsoil is blue for some reason. But yeah, it's very historic reasons for colors. But this is an engineering output that is a pre-information that will go into what Cameron's model does. This is like the behind the scenes.
Any other questions?
I was just gonna ask, I guess, have you done any quantification of the time saving and all those criteria you established to compare the traditional template-based model with this pyramid or 3D linear that you call it?
Not a formalized study, but proof of concept by the fact that we managed to save a few $1 million in budget, because the budget originally was catered for 50,000 hours of creating cross sections. I was able to create it within a day because it's from the program. So there are and then those hours became modeling hours. So there's realistic time savings based on if the initial job is budgeted to do methods in the traditional way, and then you do it via this way, then you'll see the result on the fact that you've saved budget and hours. But no, I wouldn't say a formal university study has proven that two projects parallel, one will be doing things the old-fashioned way and one doing things the new way. It's usually intuitive by the time the outputs come out that yes, you have saved time, and time is the money factor.